and just follow me around as we're going, okay? All right, everybody, I'm going to teach you how Lewis structures work and some of the other things you might need to know in order to do lab. So with Lewis structures, the main goal we have is we're going to take a molecule and we're going to try to figure out how many electrons does it have, and at what point does everything have a full octet, or it's a duet if you're a hydrogen, okay? So for instance, let's take a simple molecule, such as methane. We have CH4. Now the first thing you need to do is you need to figure out how many electrons this actually has. So carbon has, one carbon, 4 electrons in its valence shell. We can see this by looking at the periodic table. 4 electrons. We have hydrogen, 4 of them. Each hydrogen has 1 electron. Multiply that by 4, we get 4 electrons, okay? We add this together, we find that our actual amount is 8 electrons. Now, what would it look like if all of these atoms were by themselves, separate from each other, and had their full octets or duets in the case of hydrogen? Well, carbon wants an octet. So we take 1 times 8. We have 8 electrons. And then for the hydrogens, we have 4 times 2. Also gives us 8 electrons. To note, the rule for this is everything wants 8, except for hydrogen, which wants 2, and boron, which wants 6. Everything else wants 8, okay? Now we add these together, and this is our desired. So we have our actual and we have our desired. Our desired gives us 16 electrons, okay? Now we're going to take the difference between the two. So we have 16 electrons minus 8 electrons equals 8 electrons. Now, if we divide the number of electrons we have by 2, we will now know how many bonds we need to have for a Lewis structure. So if we have 8 electrons needed from our desired to our actual, divided by 2, that's 4 bonds. So if we have CH4 over here, we now know that we need C, and we have these H's around it, and we need to make 4 bonds. Now in this case, I think we can all see what we need. We need 1, 2, 3, 4. And this just means it's coming out of the board. This means it's going into the board. I'm trying to draw this in 3D on a 2D plane, right? So we found our actual, our desired. We took the difference. We got our number of bonds. We drew this structure. Simple enough. What if I take a little bit more complicated of an example? How about now we do another one that you might see during lab. NO3 minus. So for this one, we're going to start with the exact same problem. We're going to start by getting the actual number of electrons that we have. So with our actual, we have 1 nitrogen, which is 5 electrons. We have 3 oxygens, which is 6 electrons per oxygen times 3, gives us 18 electrons. And then this is a charged molecule, minus 1. Which means we have an additional 1 more electron. We add them all together, 24 electrons. Now, the N needs 8 electrons, and each of the O's needs 8 electrons. So this means we need 32 electrons. This is our desired, right? So now if we take 32 electrons minus 24 electrons, we'll find we get 8 electrons divided by 2. We have 4 bonds in this molecule. Okay, well let's try to draw it. We have N. It's probably going to be the one in the center since there's one of it and a few of something else, right? We have O, O, O. What's the problem? We only have 3 bonds. So we're going to need to do another bond on one of these. Doesn't matter which one you pick. I'm just going to pick this one. And then let's fill in the rest of the electrons. Because remember, everything here needs to have an octet. So this currently has 4 electrons on it, because each bond is 2, right? So we need to give this 2 lone pairs. This already has 4 bonds. It's good, right? And then we need to give this oxygen 3 lone pairs. And we need to give this oxygen 3 lone pairs. Now, you might think this structure's done. Well, not quite. We haven't done charges yet. First off, you put this in brackets. This is a charged molecule. That's the proper way to draw it. It has a charge of -1. What about the effective nuclear charge on each nucleus? You might ask, what is that, Ben? Well, let me show you. So, I'm just going to erase part of this here. On the periodic table, we have a distance that we are from the noble gases. So the noble gases are over here, right? We have fluorine, we have oxygen, we have nitrogen, we have carbon, we have other stuff, but boron's an exception. We don't really want to care too much about that. Boron, just know it's going to bond 3 times, usually do 3 hydrogens, doesn't have lone pairs, don't overthink it, all right? But these other ones, we want to count the distance from the noble gases. So fluorine is 1 away from noble gases, oxygen's 2, nitrogen is 3, and carbon is 4. Now what does this mean? Although we can bond like this, just because you can make a molecule doesn't mean every atom in the molecule is happy. In fact, a lot of these ones aren't, because each of these has a specified number of bonds it likes to make based on the number of electrons it has and how covalent sharing works. Fluorine and all other halogens like to make 1 bond. Oxygen likes to make 2 bonds. Nitrogen likes to make 3 bonds, and carbon likes to make 4 bonds. So over here, we see that this oxygen has 2 bonds. This one's good. Its charge is 0. However, this oxygen, it only has 1 bond. So since it has 1 less bond than it likes to have, it has a negative charge. Same thing over here. This oxygen has 1 less bond than it likes to have. So it has a negative charge. Nitrogen, we see, likes to have 3 bonds. But here, it has 4 bonds. So it has 1 more bond than it likes to have. So it has a positive charge. 1 minus 1 minus 1 gives us our total charge of -1. Now you notice I could have done the same thing with CH4, but it was unnecessary. It was unnecessary because carbon was already bonding the 4 times it likes, and hydrogen always just bonds once anyway. You need to do this when you're doing stuff that's not just hydrogens and carbons. Because even if there's not a charge up here, there could still be charges within the molecule. It just means that they're balancing out to 0, so there's no need to write it within that charge. Make sense? So we have this, we've learned how to do this. Now a few other things that you might see in the report. It might ask you about the molecular geometry and the electronic geometry. So let's go through the molecular geometry first. Let's say we have a molecule just goes in a straight line, doesn't matter what it is. That's going to be linear in geometry. So that's going to be linear whether it's in molecular geometry, whether it's in electronic geometry. The difference between electronic and molecular geometry is molecular geometry understands that lone pairs are not the same as bonds. In the electronic geometry, it does not differentiate. It thinks they're the same, even though they're not technically. But regardless, if you are in a straight line, you're going to have linear geometry. Sometimes you'll get things within the same plane that bond 3 times. An example of this might be BH3, or boron with 3 hydrogens, right? This is going to be trigonal planar. And that means we have 3 bonds, but it's all within the same plane of space. It's not 3D, it's 2D. Things get a little bit more interesting when we get to having 4 bonds, all right? So if we have 4 bonds, there are 3 different variations we can have. We can have this one, which is tetrahedral. And that's if we have no lone pairs. We can have this one, which is trigonal pyramidal, and this one has 1 lone pair. And lastly, if we have 2 lone pairs, we can get something that's like water. So we can get this, which is bent. Now, these are the molecular geometries. So you have tetrahedral, trigonal pyramidal, and bent for things that have 4 bonds and or lone pairs. note, if you're doing the electron geometry of it though, electron geometry doesn't differentiate between whatever molecule you have in its bond and the lone pair. So in that case, we are just going to say it's the same thing as tetrahedral. So if you have 4, it's always going to be tetrahedral. Note, it's not entirely accurate for me to draw these as a bond and then 2 dots, because a bond is technically 2 dots just connected, right? I'm just doing it for illustrative purposes. More accurately, it would look like this. Okay, we have our dots kind of just sitting in space, all right? So that kind of gives us an idea of what we have for our geometries. And what was the other thing that you guys didn't have for the table from lab? The first thing.
The number.
Yeah, what was the name of the number?
Steric number?
Yeah, the steric number, yes. So the steric number is the number of groupings that is around something. So if you have something like this, it's just a big linear chain. This has 2 groupings around it. 1 grouping, 2 grouping. If there were lone pairs, that would count as well. But this is a 2 steric number. It has 2 groupings around it. This would have a steric number of 3. There are 3 groupings around it. This would have a steric number of 4. 4 groupings. Same here, same here. So it's going to be the number of groupings of things around it, whether they're bonds or they're lone pairs. Where it gets interesting is if you give something like, let's say, and this is one of the ones you have in lab, C2H4. You pick one of the C's to be the central atom, doesn't matter which one. And you find it has 1 grouping, 2 grouping, 3 grouping. This double bond still counts as the same grouping. The steric number is 3, not 4. So this would be 3. Likewise, if you get to a triple bond, you're more likely to have a steric number of 2. So remember, single, double, and triple bonds, the steric number does not differentiate between any of them. All right, we can end the video recording at this point.